So today we are going to talk about BME280 sensor with STM32 NUCLEO using STM32CUBEIDE. So in this session we will learn how to interface this BME280 sensor with NUCLEO board and program it using STM32CUBEIDE and Hall libraries. At first I will briefly introduce you to the BME280 sensor. Then interface it with our STM32 and program it for temperature, pressure and humidity measurement using STM32CUBEIDE for demonstration purpose. Okay. So for demonstration purpose I will connect and BME280 sensor and we will able to see the output in the PuTTY software as like in the before session. Okay. So let us move to this. So this is how BME280 sensor will look like. So the BME280 sensor is used to measure readings regarding ambient temperature, barometric pressure and like relative humidity. It is mostly used in web and mobile application where low power consumption is key. This sensor uses like I2C or SPI to communicate data with a microcontroller. Okay. So although there are several different versions of BME280 available in the market, the one we will be studying using this one is I2C based communication protocol. So you already know how to use I2C and how I2C actually works, right? So with BME280 and the STM32 NUCLEO acts as a master and BME280 sensor acts as a slave because it is an external device that acts as a slave. So the NUCLEO communicate with the BME280 sensor through this I2C protocol to get the temperature, barometric pressure, relative humidity and the altitude. So this is how the pinout will be. You will be like have 4 pins. One is for VCC, another one is for ground, clock, data. So now let's move to the project setup. Okay, so now you can go to the system core or CC, HSC, crystal ceramic resonator, and then go to connectivity, I2C 1, I2C, and go for parameter settings, and then go to I2C speed mode, change this to fast mode, and then go to connectivity USR2 asynchronous and then go for clock configuration HSC PLL clock and here 8 and here 72, hit enter and now save this project to generate C++ perspective. Okay, so here I am going to define one thing, which is define BME280 address, which is nothing but 0x76. So this defines the I2C address of BME280 sensor. In I2C communication, each device has a unique address. So the address 0x76 is the default for the BME280, but some sensor may have 0x77. Okay. So now here I am going to do one more thing, which is type def structure. Okay. So here I'm going to give like unsigned integer 16 underscore t, here digit underscore t1. Okay, so this is how I'm going to give, like, let me copy this, and instead of t1, t2, over here t3. Okay, again unsigned integer 16 underscore t, digit underscore t1. Okay, so here let me copy this, p2, p3, p4, p5, p6, p7, p8 and p9. Okay, and same thing I'm going to give, instead of p1 I'm going to give like h1. h1. So instead of 16, 8 underscore t. Let me copy this. So h1, h2, h3, h4 and h5. h6. Okay, and after this here BME280 BME280 underscore calib. Okay, so this structure stores the calibration data that needed to correctly interpret raw data from the BME280. So calibrations values like digit T1, digit P1, digit H1, that are all coefficients that the sensor provides. So which are used in compensation formulas to convert raw sensor data to the meaningful value like temperature, pressure, humidity. That's why I mentioned it over here. And after this again BME280 underscore calib underscore data. Okay, so this variable calib data holds the calibration coefficients for temperature, pressure and then humidity. And then we can scroll it down, and over here I'm going to write a few lines. Okay, so user code begin, inside I'm going to write like void BME280 underscore read data, instead I'm going to pass void, and then again void read calibration data. So inside also I'm going to provide void. Okay, and then unsigned integer 8 underscore t I2C underscore read. So instead I'm going to pass unsigned integer 8 underscore t reg, and then void I2C read multiple, instead I'm going to pass unsigned integer 8 underscore t unsigned integer 8 underscore t data, and then unsigned integer 16 underscore t length, and then float type compensate temperature. So integer 32 underscore t ADC underscore t. Okay, so same wise I'm going to give it for the remaining two, like, so instead of temperature, pressure. Okay, so here integer 32 underscore t, ADC underscore p, and then we need to pass float temperature. Okay, and then again this is for humidity. So let me copy this and paste. Instead of pressure, humidity. Okay, so instead of P, H, and then float temperature. And after all this, integer underscore write, instead I'm going to pass integer file char pointer. Okay, and then integer len, which is nothing but len. So inside what I am going to do is that hall UART transmit HUR2 unsigned integer 8 underscore t, and then pointer comma len. So here we need to provide that pointer over here. Okay, len, and then hall underscore max underscore delay, and then return that len. Okay, so this write function redirect the output of printf to the UART. So it sends the string or data through UART2 using that hall UART transmit function, allowing the output to be viewed on a serial terminal like putty. Okay, and then we can go for the main function inside. After all this, here I am going to add one more line like read calibration data, and inside while I am going to pass BME280 read data, and then hall delay of just 1 second is enough, and scroll down. After this static void mxgpio initialization, there is a thing called user code begin for. So inside I am going to pass void BME280. In the beginning itself we have mentioned all these function name, right? So serial data, read data, inside I am going to pass that void. So here unsigned integer 8 underscore t data as an array of 8 I am going to pass. And then I2C read multiple. So inside I am going to pass the address 0 cross F7 data and then 8. So this will read 8 bytes of data starting from the register 0 cross F7. So these 8 bytes contain the raw temperature, pressure and humidity data from the BME280 sensor, right? And then integer 32 underscore t ADC underscore t, which is equal to data. Here I am going to give like 3, okay, which is less than 12. Okay, and then I am going to use or data 4 not less than, this is left shift, right? Data 5 4. Okay, and then like this I'm going to give again. So instead of here T, go for P, and here H. Okay, and over here I'm going to pass 0, this is 12, and instead of 4 we can give 1, and over here instead of 5 we can change this to 2, and after this here data has to be in like 6, and then this to be 8, and then this to be 7, and we can delete all the remaining things. That's it. So these variables store the raw data for temperature, pressure and humidity respectively by combining these multiple bytes. And after this again, float temperature is equal to compensate temperature ADC underscore T. So likewise we need to give for the remaining two. Float pressure P temperature, right? So same thing for humidity. Humidity, and over here instead of P, let's change this to H. Okay. So these functions use the raw data ADCT, ADCP and ADCH and the calibration data to calculate the actual temperature, pressure and humidity. Now let's using printf temp percentage 0.2f. Okay, degree Celsius, comma, pressure, which is also percentage 0.2f, which is HPA, which is nothing but the unit hectopascals, right? And then humidity percentage 0.2f /r/n. Okay, and then at last we need to give like temperature, pressure, humidity. Okay, and after this, here we are having some bug. Okay, so we need to enable that printf in the project, right? So let's do it in the last part. So void read calibration data void. So inside unsigned integer 8 underscore t data 24, and then I2C read multiple inside addresses 0 cross 88 data 24. Okay, so this read 24 bytes of data starting at register 0 cross 88. So this contains the calibration coefficient needed for compensating the raw data. So these are used later for calculating the correct pressure, temperature and humidity. And then float compensate temperature unsigned integer 32 underscore t ADC. So inside what we need to do is that I just going to give return ADC underscore t, which is divided by 100.0. That's it. So this simplified calculation, the raw data, the raw ADC value is divided by this 100 to get the temperature. So in a complete implementation, this would use calibration data for more accuracy. Okay. So the same thing will go for pressure. We need to just, instead of temperature, pressure. So unsigned integer 32 underscore t ADC, this is for P, and then float temperature. Okay, and then inside ADC P and 250 6. So this raw data ADC value, which is ADCP, is divided by 256 to get the pressure. And likewise, this is for humidity. So we need to change this to H, and over here 1024, and we need to change this also, right? So the raw ADC value of ADCH is divided by 1024 to get the humidity. And after this, again void I2C read multiple unsigned integer 8 underscore t, and then unsigned integer 8 underscore t, and then unsigned integer 16 underscore t, inside hall I2C mem read H I2C1 BME280 underscore address I2C memory added size underscore, which is 8-bit data length delay. That's it. So here this hall I2C mem read, this one, this function read multiple bytes from I2C device starting at the specified register. It stores the data in buffer data, and coming to the length, the number of bytes to read from the BME280 sensor. So let me build this. There is some error for all these things. Go for this project. So let me, maybe there is some mistake in the function name. So let us copy that thing and paste it over here. So down we have any. This is for humidity one, right? For humidity. Underscore save and print. So no error. This is how you can write the program for BME280 sensor, right? And now let me show you the output. I have already recorded the output video. So you just need to connect your BME280 sensor with your STM32 board, ground to ground, VCC to 5 volt, and there is already clock and data pin is present in the STM32, right? So you have to connect the clock to clock pin and data to data pin, and after that you will get output like this. So you will get out and open the PuTTY software, and you will get the output like this. It will print temperature, pressure, and then humidity like this. This is how you will get the output. So you can convert this masterclass into 1 month internship on STM32. So the actual amount of this 1 month internship is for 1,999, but there is a discount amount which is available for you, which is only for 799. So this is the registration link. And in this 1 month internship, you will get 90 days of live plus recorded session, 30 days of presentation for download, 5 project source codes for download, 1 month internship certificate, participation certificate, 90 days of access to the courses, 4 hackathon live sessions, and you can join to the community group. And also there is a 3-in-1 bundle course is available for you. So in the lineup you can choose any 2 courses by your own. STM32 is a default one, you can't change that. So the actual amount of this bundle course is for 3,000 rupees, but there is a discount amount which is available for you only for 1199. So this is the registration link to register for bundle course. And in this bundle course, you will get 90 days of live plus recorded session, 90 days of presentation for download, 10 project source code for download, 3 internship certificate, 1 year validity to the courses, hackathon live sessions, and you can join to the community group, and you will get assignments and mock test. So while making your payment, don't forget to add the courses that you want in the domain tab. So this is all about today's session. Thank you.